Okay, we're going to do a couple of moment of inertia problems. So first we have this setup. We have these four masses. We're assuming these little rods here are massless or very low mass. And we're assuming that these four balls are point particles. We're going to treat them just like they're points at their center of mass. And we're going to do the moment of inertia around three different axes. So part A here, we're going to find the moment of inertia through the center of the square perpendicular to the plane. So our axis of rotation comes through this point and points out of the screen towards you. So the thing is rotating around like this. Then the moment of inertia is the sum of the masses times each mass's distance from the axis. So we need to find all four of these distances. Well, it's a square. They're all going to be the same, and we'll just use Pythagorean to find that. So each of these sides of a triangle would be 0.2 meters. So the hypotenuse of this triangle would be 0.2 times square root of 2. That's the distance from this point, our axis of rotation, up to this mass. So we're going to take each mass times that distance squared, add all four of those up. They're all four the same. So that's just 4 times the mass times the distance squared. And we get this value in kilograms times meters squared. Remember, moment of inertia is the rotational equivalent of mass. It's a measure of how hard it is to get something to rotate. Okay, part B, we're now rotating around this line, AB. So the thing is going to rotate around this line. So now my distances from the axis of rotation will be this distance here, which is half the side, 0.2 meters. So I have all four of these are the same distance away from the axis of rotation. So I wrote up 2 of them. There are 4 of them. This distance, and so forth. And they're all the same. So it's 4 times the mass times the distance squared. And we get this different moment of inertia. It's a smaller value. It's easier to make the square rotate around this axis than it was around the point at the center when everything was rotating in the plane. And then part C, we're going to draw an axis through, say, these 2 points here and rotate everything around. So my axis will come through like this. Or I drew it this way. The axis will be here. It is this way. Here's the axis. So these 2 points, here and here, lie on the axis. Their distance is 0. They contribute nothing to the moment of inertia. Their R is 0. These 2 points here and here are 0.2 square root of 2 away from the axis. So adding all 4 of those up, 2 of them were 0. We have these 2 that were 2 times their mass times their distance squared, and we get this moment of inertia. Okay, those are all discrete cases. We have point masses some distance away. Now we'll do continuous cases. So we have a rod, a thin rod. We're going to rotate it around an axis of rotation perpendicular to the rod through the center of the rod. Now we're going to have to do an integral. This formula should have a squared in it. That's a typo right there. See, we have it there. I'll fix that in the PDF document, but that should say r squared. So the moment of inertia here is going to be our density, which is constant here. This thing has constant density, times the distance of some point away from the axis, dx. So here rho is just the density of the rod, the total mass over the length. My distance from the axis of rotation we'll call x, and then my limits will be, if this is x equals 0 here, negative L over 2 up to L over 2. So the moment of inertia will be this integral. And if we just do the integral, antiderivative of x squared is x cubed over 3. So there's our 1/3. Integrating from negative L over 2 to L over 2, a little bit of fraction work, we get mL squared over 12. Now we want to do a similar problem. We're going to take this rod, but we're going to find the axis of rotation, or we're going to set the axis of rotation at one endpoint and find the moment of inertia around this axis. So this is the problem we just did. Now we're going to do this problem. We could start over and do an integral again. It's not even a bad integral. We just change our limits of integration. Now we would be integrating from 0 to L. Or we can use the parallel axis theorem. And that says the new moment of inertia is take the one through the center of the mass, the one we just found, and add on the mass times the distance we move the axis squared. So I move the axis from the center over to the end. I move the axis L over 2. So here's my center of mass, moment of inertia, plus m times the distance I move the axis squared. And now we just clean up our fractions, get a common denominator, and we get this value here. So that is the moment of inertia around this axis. Notice this one is bigger than this one. It's harder to make this rod rotate around an endpoint than it is to make it rotate around the center.